On September 3, 1970, a supercell moved over Coffeyville, Kansas, producing one of the most violent severe weather events in the region's history. The storm's high-velocity updraft generated a hydrometeor of a scale that had previously existed only in theoretical models. The recovered stone was officially verified at 766 grams, with a maximum width of 14.48 centimeters. Gravity pulls an object of that mass to an estimated terminal impact velocity of 47 meters per second, or roughly 105 miles per hour. This velocity results in 846 joules of kinetic energy, a force equivalent to dropping a 1.5 kilogram object from the top of a 15-story building. This specific amount of kinetic energy is capable of penetrating residential roofing and causing catastrophic structural failure upon impact. The Coffeyville specimen demonstrates that at the upper limits of storm intensity, precipitation behaves as a ballistic payload, representing the extreme physical boundary of atmospheric force. The existence of such a mass creates a paradox. A 766-gram volume of water is heavy enough to fall immediately, unless the storm can provide an equal and opposite force. For ice to grow to this size, it must remain suspended within the cloud's growth zone, where temperatures range strictly between -10 and -30 degrees Celsius. As long as the stone is held within this thermal band, it continues to accrete mass by colliding with supercooled water droplets. The physics of this suspension follow the terminal velocity equation, calculating downward gravitational pull. To prevent falling, the upward mesocyclone draft must equal this downward velocity. Suspending the Coffeyville stone required vertical winds between 105 and 133 miles per hour. Giant hail serves as a physical proxy for these vertical winds, providing ground-level evidence of the aerodynamic extremes occurring within the mesocyclone. At the National Center for Atmospheric Research, scientists used thin sectioning to study the stone's internal architecture, revealing a chronological record of its growth. These polarized views show distinct bands, starting with the opaque, milky ice of dry growth. In colder regions of the cloud, supercooled droplets freeze instantly upon impact, trapping air bubbles that give the ice its cloudy appearance. This contrasts with wet growth layers, which are identified by their high-density, clear ice. During wet growth, high accretion rates create a liquid film that freezes slowly, allowing air bubbles to escape and creating solid, transparent ice. Forensic analysis of the Coffeyville stone revealed that its final 2.5 centimeters consisted entirely of clear ice. This thick outer layer confirms it spent its heaviest growth phase in hyper-concentrated liquid water, where temperatures remained near freezing. These ice bands function similarly to tree rings, preserving a history of the updraft's changing liquid water density as the stone evolved. This data was instrumental in addressing the yo-yo theory, a long-standing misconception in hail formation. It was once believed that giant stones required dozens of vertical cycles, rising and falling through the cloud to accumulate their distinct layers. To test this, researchers mapped the stone's trajectory by measuring the ratio of deuterium to oxygen-18 within the ice. Because the isotopic ratio in cloud water decreases predictably with altitude, the chemistry of the ice reveals the stone's height at every stage of its growth. The isotopic mapping of the Coffeyville stone showed a steady, single-pass trajectory through the storm. If the stone had cycled vertically dozens of times, the isotopic data would show erratic oscillations. Instead, the steady progression disproves the multiple cycle theory. Giant hail is the result of a single, sustained suspension within an organized updraft, not a series of chaotic bounces. The stone's macroscopic shape provides further clues into how it maintained its position in the sky while rapidly gaining weight. Rather than a smooth sphere, the Coffeyville stone was highly asymmetric, characterized by distinct protruding lobes. These icicle lobes form when supercooled water freezes preferentially on surface irregularities rather than spreading evenly across the core. The symmetrical distribution of these lobes suggests the stone was tumbling rapidly and steadily as it grew, allowing for uniform accretion on all sides. As these lobes grow outward, they intercept water droplets more efficiently than the stone's core, creating a geometric feedback loop that accelerates mass accumulation. This irregularity allows the stone to grow faster as it expands, maximizing mass before gravity eventually overcomes the force of the updraft. Generating updrafts exceeding 100 miles per hour requires a specific atmospheric architecture that only occurs under precise conditions. These events cluster in specific corridors, such as the U.S. Great Plains and the Alberta foothills, where geography interacts with the air mass. The process begins with a synoptic capping inversion, a layer of warm air aloft that prevents early convection and traps heat near the surface. High levels of moisture and convective available potential energy, or CAPE, build up beneath this cap throughout the day. The final ingredient is topographic, easterly upslope flows that are physically forced upward as they encounter mountain ranges. This mechanical lift breaks the inversion cap, releasing the accumulated instability in a sudden, explosive vertical burst. Giant hail is a geographically specific phenomenon, representing the moment where terrain-driven lift releases a region's accumulated thermal energy in a concentrated vertical release. Comparing the 1970 Coffeyville stone to more recent record breakers reveals that physical width is an incomplete metric of a storm's power. The 2003 Aurora, Nebraska stone reached a 7-inch diameter, yet it weighed only 1.33 pounds, significantly less than the narrower Coffeyville stone. This means a physically larger object can actually transfer less kinetic energy upon impact. This discrepancy is driven by density. The Coffeyville stone was composed mostly of solid, wet-growth ice, while the larger Aurora stone contained a higher ratio of porous, air-filled, dry-growth ice. Both were eventually surpassed in 2010 by the Vivian, South Dakota stone, which weighed 1.94 pounds with an 8-inch diameter. Because impact force is driven by mass, the liquid water density of the updraft, rather than simple diameter, is the true indicator of a storm's vertical intensity. A giant hailstone is a temporary artifact that begins to degrade and lose its data the moment it reaches the ground. However, its internal layers and morphology preserve a history of the storm's thermodynamics that would otherwise remain invisible to surface instrumentation. Analyzing these specimens allows researchers to ground the abstract science of meteorology into physical evidence. Giant hailstones serve as physical flight recorders, providing tangible proof of the absolute mathematical boundaries of severe